So we have basically three types of water, excuse me, three. Got one too many fingers up there. We have this kind of scenario. We have gravitational water. Now, gravitational water is that water that is pulled down through the root zone by gravity. So it doesn't take a lot of energy to get this water moving, and it's simply being pulled down by the gravitational pull on everything that's on the surface of the earth. There's also another kind of water called capillary water. Capillary water is water that moves sideways. So this water is going down. That water is moving downward due to the force of gravity. Capillary water is saying, oh, I'm looking for the least energy location to go. So sometimes it might be sideways. As I come down, I'm a drop of water working down through the soil, and I hit one of those platelets. Instead of going around it this way, I might go sideways across the surface of it. Because it's drier over here and it's wet here, so I'm going to go where it's drier. There's a force pulling me toward the dry area. Those clay particles want water, so they're attracting water sideways. And so this capillary water, it's going sideways. It can also go up and down. All it's doing is looking for its path of least resistance. It's going toward the lowest energy level in the soil, wherever that might be. Could be sideways. As the soil starts to dry out from the surface down, because that's how soil dries out, the top dries out first, and as it dries out, then capillarity says, whoops, I'm getting dry up here and I'm really wet here, so I'm going to move some of my moisture to the surface. So we can get capillary water even moving upward in the soil. Okay? So it can move in all directions, but generally we think of it lateral movement with capillary water. Now, capillaries means it follows the capillaries in the soil. That means the little tubes, the little holes that it can work its way through. Yes?
How does it go uphill if we have gravitational water?
It fights gravity. The question is, how does it overcome gravity to pull up? The osmotic pressure in the soil, there's a force on those clay and silt particles that attract it. They have a molecular reaction that literally are sucking the water toward them uphill that overcomes the force of gravity pulling them downhill. So it can happen. Obviously it'll move a lot quicker going down than it will. It takes quite a bit of energy to pull it up. But that's how, hey, take a towel, spill water on the table, put a paper towel on there. You got a little drop of water that big around, put a paper towel, where does it go? All of a sudden you got a blotch that big on the paper towel. That's capillary. It's finding its point of least energy, so it just goes sideways laterally. And if you have the towel kind of standing up on end, it'll come up part of the towel too. It might raise up on the towel an inch or so. So that's capillarity at its best, just doing its thing. And you do that every time you use a towel to clean up your counter. You're just proving capillarity works. Pretty nifty. Then we can squeeze all the water out of it and do it again. Dry it out, do the whole thing all over again. And that's what soil does. Put water on it, let it use it up, it dries out, put more water on it, it kind of acts like a big sponge. And you get a sponge wet, the sponge, take a sponge on the countertop, it'll be wetter on the bottom of the sponge but on the top of the sponge, but the whole sponge will be wet. If you have a nice thick sponge, get water in it, water will work its way clear to the top of the sponge. If you just set it on a puddle of water, that's capillarity. That's just what's happening. And it's just the molecular attraction of the particles within the sponge, or in the soil in this case, that is pulling the water upward. It's saying, hey, I'm too dry, I want some of that water, and I have the ability molecularly to attract it. And so it pulls it toward itself. And sometimes that's up. but it's a lot easier to go sideways. Now when we get into drip, we really see that happening. Point applied drip, you know, we're putting one little drop of water on the surface of the soil, and then we just let it start spreading sideways. And pretty soon you get a great big ball of water around it. So if we had a ground surface over here, we put a point emitter with drip. It's a classic example. A little drip tube here with an outlet port, and we put a drop of water here, and we just keep dripping water. It doesn't just keep going straight down unless it's pure sand. What happens in pure sand is it just keeps going straight down. You get a little tube of water straight down, about 6 inches in diameter. There's a name, they call it stovepiping in the drip industry, and when we get into drip, we'll talk more about that. But in most soils, there's clays and silts, and this thing, as these drops, you know, this thing will spread out like this, and it'll form kind of like an onion shape of wetted area. And pretty soon you got an area like this that's wetted, but it's only dripping right there. Gravity's pulling her down, capillary action's moving it sideways. And that's what you end up with. You end up with this big wetted area. That thing could be 4 or 5 foot in diameter from a drip of water. That's pretty typical. Typical silt soil will have about a 4-foot diameter ball of moisture under a single drip emitter. That's pretty standard. You know, it's kind of an average thing. So it's pretty slick. That's capillary action. And we call that capillary water, where it moves sideways.